All right, so we are going to start by looking at our first module, regression module, um, and talking about regression and bivariate and multivariate regression. So we'll start off by talking about what regression is. So it's a statistical tool used to describe and predict data. So data gathered for research purposes contains predictors and sometimes multiple predictors and outcomes. Regression allows us to analyze the relationship between these variables, and this can be very simple or complex. To simplify this, when we have one variable and we want to calculate its outcome, the best guess is usually the mean, but the mean isn't always very informative. So we can use predictors to better predict the outcome. For example, a common example we use in class is the level of education a person has and how that can affect or can give us an idea, help us predict what that person's salary might be in the future. We assume that there's a positive relationship between education level and salary. So this can give us a hint as to how much money a person can make in the future. So education level would be one of the predictors in this situation. However, one single predictor oftentimes doesn't really do a great job at predicting the outcome, so we need many predictors. Um, Robert Abelson's 1985 article on the variance paradox showed us that one individual predictor, like a person or a player's batting average, doesn't always help us guess the success rate of the team due to the fact that in order to win games, multiple players need to have a high batting average as well. It's not just the one individual player. So it's just one piece of the puzzle, and it requires us to take a look at other predictors in order to understand and predict if a team is going to have a high success rate. So we'll do that with body mass index and other predictors that we found to potentially predict what a person's BMI might be. So regression is based on the ordinary least squares method, which finds a simple linear regression of data, meaning it models a linear regression between one or more variables. Okay, so um, as I mentioned, we're going to look at BMI and the factors that can affect it. We want to have a healthy BMI, and we believe that there are certain variables that we can use to calculate or predict whether we will have what our BMI is going to be. So that's going to be our Y variable. And the first predictor we want to look at is parental BMI. So some research suggests that parental BMI has a strong positive correlation with somebody's own BMI. The larger the BMI of your parents, the more likely that yours will also be high. So we expect a positive correlation or parental BMI to be a positive predictor. And we want these predictors to be orthogonal, and we want to be able to predict, oh, yeah, we want them to be orthogonal and to be useful in helping us predict whether someone will have a healthy BMI. So we can add other predictors, such as something like socioeconomic status. But it's important to note that these predictors use different scaling methods, and that requires standardization later on in order to be able to compare them. So Schultz's 2010 article informs us that standardizing beta coefficients is going to allow us to compare two different scales of measurement, which is what we're doing here. We wouldn't be able to compare all of these different predictors if it wasn't for that. So and moving on with this comparison, this bivariate regression model, we're going to do first a quick plot to help us visualize the relationship. Here we go. We've got a little bivariate plot here. So right here, this is our line of best fit, and it indicates a positive correlation, positive slope, like we suspected. So again, this looks pretty good. We see an overall positive correlation. There doesn't seem to be any values that are too far away, perhaps maybe this one. So yeah, the higher the BMI of the parent, the higher the BMI of the person. Okay. So using the numbers as summary, it's going to help us to get more detailed look at the data and to understand the relationship more deeply. So first we'll look at this intercept here. This is what would happen if the y value were 0. That means that if our y was 0, then our parental BMI or our BMI would be about 2.2. And then this indicates that for every unit of change in body mass index, we expect a 1.1 or 1.05 increase. So in BMI. So these are our parameter estimates. And the bivariate regression equation on this would look like this. So the BMI would equal 1.1, which is just an estimate at this 1.05645, times x, which is our parental BMI, plus a 2.2-ish, which is our intercept. So that's our bivariate regression equation. And we were talking about parameters, and these parameters each have a standard error. And this indicates how different the population mean is from the sample mean. It gives us an idea of how much our mean would vary if we were to repeat the study with new samples from a population. So standard errors can be affected by many different things, specifically something like sample size and multicollinearity. So if we have multiple predictors, like we will have in the future, we expect these to change. Also, using the standard error, we can calculate the t-values by taking the standard estimate and divide it by the standard error, and it gives us a 7.7 and about 33, respectively. So also here, we see that the parental BMI is a significant predictor because it is smaller than the 0.05 p-value limit. So we're able to reject the null in this case with this predictor. And also the adjusted R squared over here is about 85%. So what this means is that the parental BMI accounts for 85% of the variation in BMI, which is a really big portion. And we'll see what happens to this R squared calculation as we add other predictors. And then just to kind of look at the data a little bit more, we've plotted some diagnostic plots, and I guess looking at this QQ norm plot, there's some slight deviation at the tails from the expected values, but all of this is pretty close to the line and appears relatively normal, minimal S-shaped curve. So looking at this, I would say that our points seem to be relatively evenly distributed across this axis. And yeah, there's some more. There's a bit of an outlier here that's really might skew our data a little bit. So we wanted to really clean up this data. This might be one of the plot points we remove. So the predicted value over the observed is actually really close. So it seems that parental BMI is actually a really good predictor. And I think we've got a little histogram next, and that shows a really beautiful distribution here. Okay. Okay. So we want to take a look at multivariate regression. What's going to happen when we add more predictors? So we'll start off by saying David Friedman's statistical models and shoe leather article states that using a 3-variable approach can miss other factors that can make up our outcomes, such as in our model. So we have some values that are statistically significant and some that aren't. And we want to account for variance. So we really want to have some more variables in the model. So a 2-variable approach is really not enough, nor does it represent real life. Realistically, there will always be multiple variables that are affecting an outcome. It's very difficult to isolate variables, particularly in like behavioral or like medical research. So yeah, here I'm just kind of showing just the first few data points that we have. There's tons, but I just plotted the first 6, and we're using parental BMI, as we stated before, socioeconomic status, activity level, and education. So these are some of the other predictors that we're going to be looking at a little bit further. Also, we can account for shared variance among our predictors and outcome variables, which is a better example of real life using multivariate regression. And yeah, so there's just a quick little table to show some of the data that we're going to be using and why we're doing multivariate regression. Okay. So the summary, the first thing we'll look at again is our intercept, which has just very slightly changed. It's changed from 2.18 or so to 2.21, like we see right here. Also the adjusted R squared, it's only changed a very little bit. It was about like 0.852, now it's 0.8533, which means that all of these predictors account for 85% of the variance. Um, and then looking at our p-values, we've got a few that aren't statistically significant, such as education and socioeconomic status. They're just higher than the O5 level, but our parental BMI and our activity level do meet um, the requirement. They are statistically significant. Um, Looking at the VIF scores, which is the variance inflation factor, this can inform us a bit about the shared covariance or multicollinearity among our predictors. So we can see that parental BMI, however, and activity level have very high VIFs, which this could indicate multicollinearity. One thing we can do is take a look at the correlation matrix to see how these two correlate. Here we go. Um, these variables, let's see, right here, very high correlations. So certainly some multicollinearity happening here. Um, but it seems like, oops, the adjusted R squared of the entire multivariate regression model compared to the bivariate is just very slightly larger, which means that parental BMI really accounted for the majority of this variance, and it was a pretty good predictor, although it is um, um, sharing variance with the activity level. But overall, the model explains roughly about 85% of the variance, which is good, although it suffers from multicollinearity. And I would say our bivariate model was a little bit better because it also explains about 85% of variance, as we said, meaning we picked I think, a pretty good um, variance predictor. So yeah, that's just some of the plots and things that I did for the regression summary. And yeah, thank you very much.